What is up, team, and welcome back. This video will serve as a answer key to the conceptual piece of our review for the unit high dive, and this one is the assignment called sandcastles. So this is conceptual, and sandcastles will be the context of the problem. So you have access to the document in front of you. I've taken some screenshots of the problem here, and I've set up a graph already. I'll talk about it in just a second. But in other words, there's a scenario where there's a couple people. They're on a beach and they're looking to build sandcastles. They understand that the different water levels are going to potentially interrupt their plan, and so it's up to us to figure out where the water will be in relation to their sandcastles. And so there's a diagram here that the problem provides. And in this diagram, it shows you an average water line, which we will consider a value of 0, which is represented here on the graph, just a value of 0. We'll call that our x-axis. And then anything below that is going to be negative footage compared to that average line. And anything above that is going to be positive footage. So the water level could be down here, more in the ocean, which means you have a lot more beach available to us. Or the water level can be up on the beach a little bit more, which means there's going to be more water. And so essentially, we want to have more beach available to us so that way we can build a sandcastle and not have it be washed away. In this problem, the equation is given by W of t is equal to 20 multiplied with the value sine of 29t. Okay, so let's break down this equation and start off by answering question number 1. Question 1 wants us to graph the waterline function for the 24-hour period. So here on our graph, I have t in hours, and it goes all the way up to 24. And then with our height, I went up to 20 and I went down to negative 20. We'll talk about how I got those values in just a moment. But let's break this down. So this W of t looks a little bit different compared to our original function of theta that we're used to seeing. So this W of t actually stands for the water line, and I'm going to call it a function with respect to time. Okay, so this is looking at the water line, a function with respect to time. And this water line is actually measured in feet. So depending on how much water is on the beach or off the beach, it'll be determined by this function. Okay. If we recall, there's a couple different ways that we can start graphing. The first one is finding some sort of vertical shift, or in other words, a starting value. Now, this is found by finding the constant term. If we're thinking just strictly algebraically, which value in the original function will give us that. And in this case, there is no constant term. It's all part of the same expression. This is all one term, which means that our vertical shift is going to equal 0. Okay, so technically this is going to be plus 0, which makes sense because we're using the average water line um, as our x-axis, which is at a value of 0. So this water line here, or in other words, we can call this the midline, is going to be actually on this axis. So what I'm going to do here is I'm going to actually put an arrow, and I'm going to call this our midline at y equals 0. So that way you can take a look and use that as our reference. Okay. The amplitude is another value that we're going to need. And this is going to help us discover our maximum and minimum values. This is our coefficient of sine. Okay, it's going to be the coefficient of whatever trig function we have, but in this case, that's a value of 20. Okay, so we'll use this just a moment to help us look at our, what you may remember as our maximum value. So the water has to stop to a certain point. It can't just keep going on forever into people's houses. There tends to be what's called high tide, and that's the how much is occupied on the beach. So this max value for the water line is going to be the sum of the starting value and the amplitude. So that's 0 plus 20, which is going to give us a value of positive 20. Our minimum value is going to be that starting value of 0 minus our amplitude, which gives us negative 20. And so uh, if we think about this, if you're having trouble kind of visualizing what's going on, you may recall that there's some sort of you have the beach that everybody is on, and then you have your water levels with the waves and just water kind of flowing in. Okay, so there's my wave. As the water level increases, let's say it's a little bit more on the beach, right? So you have a little bit more water on the beach. Um, then our water level or the water line is going to increase. Okay. As the water line tends to go back into the water, maybe down here, and it starts to decrease, then we're going to experience a water line that is more negative. So the average could be somewhere right here in the middle, and it could be low tide or high tide. Okay. So in other words, we're graphing this low tide, high tide effect, and we need to figure out where we can put our sandcastles. Okay. And then finally, we have our period, which if we go to solve, we're going to take what's inside of the parentheses, 29t, set that equal to 360 degrees. You remember the inputs of a sine function need to be an angle measurement. So either something in degrees or radians. And when we are looking at a period that is in terms of something other than that, this is going to help us convert into this degree or radians. And so if we use 360 to help us look at this, and we go to solve for this, we end up with t equaling a value of 12.41. Okay, and we're dealing with hours. So I'm going to put hours. Boop, boop, boop. Okay, so what this essentially means is every 12 hours, the water line will return to its average, or whatever that midline is. Okay, so every 12.41 hours, every 12.41 hours, it will return to its midline. Okay, so let's graph this. First and foremost, we have the midline that I put down here. We have our maximum value of 20. Our minimum value is also at 20, except negative. So I'm going to take my ruler that I have here. I'm going to go ahead and put this at the 20 mark way up there. And I like to use different colors to help me create the structure of the graph. And so for this first value of 20, I'm going to go ahead and put this line. And then I'm going to come down here to negative 20. And I'm going to also put this line. I use a dotted line so that way I know it's not actually part of the graph. It's just going to be helpful for me to see. Okay. The amplitude we don't actually need to put in there. However, it does represent the distance from the midline to the max. Okay, and it's actually seen when we get to the maximum point and the minimum point of this graph. Okay, so the hardest part about this is incorporating the period because our graph looks really cool, really nice using all of these whole values 2, 4, 6, 8, 10, 12, but our period is in terms of it's a decimal, so it's not a whole number. So I'm just going to use my best guess here, and it's 12.41 is almost in between 12 and 13, so it's like right about there. All right. So what I like to do is when I'm creating one of these graphs, oops, didn't mean to do that. When I'm making one of these graphs, I really like to make sure that I break apart the different sections of the graph to make sure that I am appropriately um, spacing out my values for the maximum, the minimum, the return point, as we call it in class, as well as the midpoint. And so to make a sine function for a problem like this, I like to first mark off where a full rotation is going to be, so a full period, and then I like to continue with dividing everything in half. And so in this case, half of the 12.41 will be about 6.2. So I'm going to come over here kind of right in between the 6 and 7, but not quite 6.5. This is going to be my halfway point. And then halfway between that is going to be about 3.1. So it's just past the 3. And I'm going to use this graph now divided into a few different regions to help me create the overall um, uh, image of this sine function representing the water line. Okay, and then up here it's a little bit over 9. Okay. So, yes, I did round our period just a little bit to 12.41. So over here, we have an x value of 12.41. This is known as our period. And then right in the middle is going to be half of that period. So x equals 6.2 or roughly. And then half of that is 3.1. And then over here, we're going to kind of do the same thing. We end up with 9.3 around x equals 9.3. Okay, so I just try to divide it into 4 equal sections. So you'll see 1 section, 2 sections, 3 sections, 4 sections. And we're going to use these different regions of the graph to help us sketch out this image of this function. So if you remember in class, we discussed kind of where these points go. The first one's going to start right there on the midline. You're going to use the value that you have for the midline, the y equals 0, and then you're going to start at time 0. We're going to assume that this is starting at some time 0, and we're going to need a graph from there. The water is going to be returning at 12.41, so almost 13 hours later, it's going to return back to the same spot, but we're going to experience some high tides and some low tides in that mix. So I'm going to come up here, reach a high tide, come down. Oops. Let me see if I can make this a lot smoother. Got a high tide, come down, back to normal, go down, hit a low tide, and then come back to our starting point. Now, the image itself, or the graph, wanted a 24-hour period, which means I'm going to need to keep doing this as we continue throughout the 24 hours. And so because we're dealing with 12.41 as our period, that means the next time frame that I'm going to be coming back to the starting point is going to be at 24.82 to represent a second rotation. So that's going to be just past 24 here. So what I want to do is actually make sure that I'm appropriately looking at this graph and trying to space it out the best that I can in order for me to solve this problem. Okay, if we determine that half of the period is 16.2, then we're going to have this be added on to our full period, so a period and a half. So that way I can see kind of where this next midpoint will be. So that's going to equal a value of 18.6, right around there. And that's going to be my next value, and then I'm going to come back here. So instead of finding out what these exact values are, I'm just going to go ahead and rough estimate it. I'm going to reach a high point somewhere in between there, and then I'm going to reach a low point somewhere in between there, and then come right back. Okay. So this graph would be worth it for me, so that way I can see that you understand the flow of what a graph looks like. Now here, yes, the values are going to be a little bit off because the period itself is 12.41. So a nice sketch of this will be appropriate enough for a test or a quiz. So we have number 1 down. Great. Boop, boop. Now it's time for us to look at this. What is the highest position up the beach compared to the average that the water line will be during the day? Well, that will be our max value. Okay, so this will be 20 feet above. Okay, 20 feet up the beach will be our max. That's our high tide. That's indicated right there, or I guess in this spot. And then low tide will be minus 20 feet down the beach. Okay, which means we're going to have more sand to play on during low tide than we will on high tide. Okay, so this is we're going to have more sand down there, and then we're going to have more water up there. So we need to figure out kind of what's going to happen when it comes down to us looking at our sand castles. So it says here for number 3, I guess number 2 is done. Suppose Oceana plans to build her sandcastle right on the average water line. Okay, so right on the midline here, on the average water line. Okay, just as the water has moved below that line. Okay, so if you remember, everything that is in this region, I'm going to do it in gray. Actually, I'm going to do it in like a light green because that's what it does here for the beach. Everything below the water line tells me that I have more beach time. In green, I'm going to put. And then everything above that water line tells me that I have more water. So just to color it in so you can see it a little bit. So in this problem, it says that she would like to build a sandcastle on the average water line just as the water has moved below that line, which means that she's going to start right here, her sandcastle building. Okay, let me get like a yellow. Boom, boom. Castle. Okay, she wants to start right there. Now, what we need to figure out is how much time will she have to build before the water comes back and destroys her work, which means that we have all of this time in order for us uh, to build and maintain this sandcastle so it doesn't get destroyed. In order for us to actually discover what's the distance between these two, it becomes important that we use the period. Okay, so if we go to answer number 3, let me see if I can zoom out a little bit. If we go to answer number 3, the first thing I like to do is consider our period in terms of having one complete cycle. So the period equals one cycle. And we spoke about this in class and also in other videos. So at this point, we have gone through one complete cycle. So we want to figure out kind of this distance in between it. Well, if you notice, that goes from the midpoint all the way to the period. So this time, I'm going to say high tide, or let's rephrase a little bit. But we're going to have more water is going to be half of the time or half of the period. We're going to have more beach also half the time. So more beach is also going to be half of the period. So in order to answer this question, how much time will she have? We just take the period and cut it in half. And we can see that in this distance, we have 12.41. So what's going to happen with Oceana is she's roughly going to have around 6.2 hours to build, which some people feel like that's a long time to build one sandcastle, or I guess multiple sand castles. But she'll have about 6.2 hours to actually build it. Okay, we're going to use this same methodology to answer the next couple questions here, and starting with number 4. So number 4 says, suppose Oceana wants to build 10 feet below the average water line. So now Oceana is looking at a different type of problem. So I'm going to take my ruler out here just to help me sketch. and she wants to be at 10 below the water line. Okay, Oceana's pretty smart because she's not going to build anything above the water line, right? Then that means that she has less room to build a sandcastle. So here's going to be my best line that I can put down to represent where she wants to build for number 4. And we need to figure out kind of how much time does she have to build in order for her to continue. So it says, what is the maximum amount of time that she can have for making her sandcastle? So in this problem, I'm going to go ahead and take a darker shade of green and take a look. So she wants to start building at this time. And then she's only going to have a little bit shorter. So the region that we're looking at is this time frame here, this little capsule of time. And we need to figure out how is she going to be able to do this? And so in this type of problem, in addition to number 5, we're actually not going to do number 5 in this video. We're going to talk about that one in class. But for number 4, we want to figure out kind of when is this function, w of t, going to give us a value that is actually less than -10. Okay, so we need to kind of figure out like where is this time going to give us these values. So instead of going through and solving it, we need to discover what tools do we need in order to get to that point. And so for this problem, what we're going to do is just kind of look at the graph, and I'm going to just say, I'm not going to use the word guesstimate, but using the graph in essence to read what these values could possibly be. So assuming that I made this sketch somewhat accurate, we're going to have a value just a little bit before 7, or a little bit after 7, I apologize. So this is around 7. And then over here, it's past the 11 mark. It's actually closer to 11.5. And so using this, I'm going to just go ahead and calculate these times, or I guess estimate by reading the graph, the time in between. And so here in this problem, we're going to get a value between, we're going to look at between 7 o'clock, or I guess hour 7, 7 hour, and 11 and a half hour, which will give us a value of around 4.5 hours, which makes sense because before, to be exactly at the average line, it is 6 hours. And then now that we're below that average line, we're looking at about 4 hours. Okay, we'll talk about it in class next period. How do we officially solve a problem like this to discover the true time or the true value of this? But that will be something that we need to review and discuss in class. Okay, but I hope this helps with graphing and a little bit of reading the graph. And this is all we're going to go through for the problem sandcastles. If you have any questions, bring them to class. And with that, I will catch you next time.